exceptional capabilities in visual understanding and reasoning. So I will introduce 3 works along the line of compositionality. The first work is composing images and visual prompt in the input space, and the second work is composing the counterfactual images and captions. The third work is about composing the natural languages and scalable vector graphic code as the input to a large language model. So note that all of those work need minimal changes to the code, to the actual training and inference code. We are actually doing some. Oh, what happened? Okay, yeah. So we are actually only manipulating the input. So it's the basic idea is very simple. So let's dive into my first project called enhancing region understanding by composing images and visual prompts. So so everyone know what is GPT-4V, and most of us know what is LLaVA, which is from Haotian. So what they essentially did is that if we ignore the middle part, the input is the single image and the text prompt, and the output is just like a line of text. So the intriguing question is that usually the image can be very complex, like these things. Like how do we refer to a certain person in this complex image or a certain? Okay. Yeah. So the question is, how can we refer to a certain object or a certain person in the image? So this essentially tell us that we need a model that can understand region level information. And yeah, so existing works they mainly try to embed such regional hint into the text prompt, like they directly convert the bounding box into textual coordinate and train the language model, or they can extract the regional input features from the visual encoder, or they can learn a dictionary or discrete tokens, and then they map the positions into a grid of tokens. And by learning such positional dictionaries, the model can learn about the actual positions. But those approaches are very important shortcomings is that they can't understand diverse visual references such as scribbles or arrows. And actually, in internet, we usually use such random and arbitrary visual prompts to refer to objects. So how to solve this problem? Our solution is very simple. Our solution is just A plus B. A means the original image, B means the visual prompts. And then you can use some techniques like alpha blending. So this approach is exactly what you did in Facebook or Instagram, like when you want to send an image to a user and want to highlight some parts. Yeah, our approach is very simple. Like I said, what we changed is only about we add visual prompt to the original image, and everything is the same. So this simple change brings unprecedented benefits along several aspects. For example, it can replace any visual prompt because we annotate the image in pixel space. Secondly, we can secondly, there is no region level model design, which is the simplest approach. And thirdly, user can control the visual prompt in the text, like they can use text like marked with red arrow, or you can change it to scribble bounding box. Everything. Yeah.
Saying overlay the visual block into the image.
Yeah.
That means that you add another channel into the image, like RGB and alpha, or like your final image is still RGB.
That's a good question. The final image is still RGB, so it's like some averaging upon the pixels. Yeah. Yeah. And here is a detailed explanation about the approach. Yeah. We do the alpha blending, get the edited image and feed it into a clip image encoder. Note that the clip image encoder is also frozen. And then we do all the things as LLaVA 1.5 and train the model. So that's it. And people may be curious, what kind of data can we represent? So we do experiments among 8 kinds of visual prompts, including like mask counter, elliptic, bounding box, triangle, scribble, point, arrow, and mask. We do as much visual prompt as possible to reflect the real world referral. Also, we randomize everything like the transparency level, the shapes, the color, white scale, and direction to satisfy the real time to satisfy the open world user need. And we collect a total of 520K data, including like region captioning, describe the object in the bounding box, multi-region perception, like choose the right region, object counting, and very difficult visual comments and reasoning. Like we want to reason about the relationship of two object, like what are they going to do, why they are going to do certain things. Yeah. So empirically, our simple approach achieves the best performance up to now on diverse tasks such as object recognition, object counting, visual reasoning, and region captioning. So it means that even some simple approach can naturally embed the positional information into the image. And more importantly, we found that those previous approaches like SQL or GP4 ROIZ, yeah, go ahead.
Testing the model is frozen and you found the images to the model with counter to the image counter, and then you have a test point, or how is it evaluated?
Oh, how is that? Yeah, how it is trained, then how it is evaluated. What I mean is that during training, we convert the bounding box into the visual marker into the image.
So
That yeah.
The model is not frozen.
Huh?
The model is not frozen.
The language model is not frozen, but the visual model. So this part is frozen, but all the other parts are trainable. Yeah, for example, the orange part is trainable. So essentially, we want to leverage the language models to understand, to express the power of the visual prompts. Yeah, Tom.
Why can you get a question and answer for each visual prompt?
For a visual prompt.
For each visual prompt.
For each visual prompt.
Yeah, how can you get a question and answer?
Okay, so yeah. So for the question and answers, they are from the existing academic benchmarks. I do not curate any data set for some basic understanding capability. Yeah. Yeah, and moreover, we will later on show that the specifically designed region-specific approach like GP4, RY, or SQL, they are heavily fitted to the academic benchmark and perform very bad on freeform QA. So let's first look at some interesting examples. So such a pixel level visual prompt can ignite strong capabilities in the open world user interaction. For example, the user can draw 3 circles randomly and ask which 2 circles share the same content, and then our model can see that, oh, the 2 regions with the same content are with the red and blue circles. So the important point here is that you can randomly change the shape of the circle, because as you can see, the circle here is not perfect, and you can change the Y, change the color, change everything, and it brings more flexibility. Yeah. here is another interesting example where we have two arrows. The body are the same, but the head of the arrows are different. So we ask what is the arrow pointing to, and our model can correctly recognize the object that is pointed to. And here is an image from the GPT-4V technical review, and the here is a compositional task where the model needs to understand the circle, the arrow, and the text. And our model can successfully firstly do the perception about the containing material, and then do some reasoning about what's in the circle graph, which is pretty amazing. Yeah. Yeah, and like I said, besides the academic background, we found that in region level understanding, there is no free-form QA. Like, please explain why something happens, or please solve a specific problem. So we use human annotators to curate a free-form VQA benchmark, including 6 aspects, like recognition, OCR, relationship reasoning, and language generation. So here are some examples. For example, here the model needs to do two things. Firstly, the model needs to localize, where is the blue ellipse? After the model localize the region, then the model needs to do the math calculation to solve this math problem. Yeah. And here is a more interesting example where the model needs to localize the 3 arrows with different colors, and then they will find that, this girl, this boy, this girl correspond to 3 arrows, and then the model need to understand the social interaction between such 3 people, and then do a very long sentence and reason to explain why it happens. So, given this free-form QA benchmark, how is the performance of current region level understanding benchmarks? So, here, coordinates or RI means space, and discrete tokens means specifically designed region level large language models that I show within the red bounding box. And we found that those especially designed region level large language models receive inferior performance even compared to the image level large multimodal models. And with our view prompt, we can achieve best performance just below 64, which is a very a high bound for kind of multimodal community. Yeah. Yeah.
What is the number?
So synthesize and human means that for synthesize we use the bounding boxes to annotate, but for human we actually ask the human annotators to draw those arrows. So so I think different model perform differently upon such 2 kind of tasks. For example, here for LLaVA it performs better in synthesize, but for human it performs better in human. But roughly, I think the trend is similar. Yeah.
If I give you 20 times more compute and data, and also accumulating budget, how would you improve your model's outcome?
Okay. Yeah. So this is a good question, and my personal opinion is that current models are very smart if the capacity is enough. What smart means that if you let the model see enough content, meaning that in larger resolution, and if you let the model to reason longer, like if you use chain of thought or use a larger language model, I believe it will train better. It will perform better. And secondly, an important problem is that how do we ensure that the view prompt didn't hide the important details? Like, what if there is a big circle and it covers all the humans, and you can see nothing? So data engineering is certainly important. Yeah. Yeah. So an interesting question is an interesting question is that till now we are still using a fluent clip, and people usually say that clip is good at understanding natural images. But why Floral Clip can understand such synthesized visual prompting image so well? So evidence is that in a paper from ICC 2023, they use retrieval to find that for example, in YFCC for 40 million, there are some annotations in the clip pre-training data that have visual prompts. So yeah, I think this also answers the question about the importance of data, and I guess that our approach benefits from a more visual prompting training data, and maybe someday in the future there will be a region level clip that focuses on visual prompt understanding. Yeah, and our work has our work just released 3 or 4 months, and there are more interesting papers about visual prompt coming out. For example, Google DeepMind has they use visual prompt for robot planning, where they mark different routes as some circles and pieces, and then do the planning, then do the robot planning. Yeah, so here is my first work, which composed the image and visual prompt in the image space. But there are more things that we can do. We can also compose it in the text space. Like an interesting phenomena or an interesting problem is compositional reasoning. So, like this image said, we can compose things in image space. But what about compose different elements in text space? Like for human, given this image, you need to choose 2 options from to get the correct option. The first option is a pink scoop on the top and a blue scoop on the bottom, and the second caption is just to flip the order of bottom and top. So this question is very simple for human, because if we carefully look at such 2 objects, we can localize and then determine the best option. But we found that even the best model right now cannot handle this task. For example, here are the visual question answering from GPT-4 the currently most capable multimodal model. Yeah, here both questions are about positioning, left or right, top or down. Yeah, you can have a look at the question like the stress on the left is long and the stress on the right is short. In the same caption, we just flip the order of short and long. So GPT-4 can do some reasoning, like I showed in the in the green text, but finally it made some wrong answers. So similar thing happens for the above and below case where the final answer is wrong. So in order to systematically study this problem, we built a benchmark to understand this phenomenon. And we how do we build the benchmark? We use the existing data set with bounding boxes, and we extract the bounding boxes where, for example, the ball is completely over the clothes or the body. And here also the boy is completely to the left of the toys. So this is a very strict data set that we have ground truth, very clear ground truth answers, and then let's do VQA to test the model's performance. So, and you can see the random chance is 50, but for current models like Clip and LLaVA, they produce random chance, and LLaVA is better than random chance, but still a low, low performance. So then our next step is our positioning are the only problem that Clip is or LLaVA is best at. So we do another experiment about object counting, where we can count the number of objects in the image annotation. Like if the ground truth is 3 and 4, then we can just randomly deduct the number to 2 and 3. So the random chance is still 50-50. And here is the performance. Clip is a little better than random, and LLaVA is below the random. So we are wondering how to systematically fix this problem. Yeah. So yeah. I know your point. You are guessing that LLaVA use a larger language model, but why perform badly at Clip? So it's hard to say because if LLaVA don't have a lot of county data, then they may perform bad on this task. Yeah. So yeah.
So why can Hopkins say better than
So firstly, I think those both models they perform bad, but yeah, firstly both models perform bad, and secondly maybe in clip pre-training there can be some county data like in Instagram, but in LLaVA, if I remember correctly, there is no specific data about the object. How is this true?
I think there is also a reason that these two methods are not evaluated in the same way. Where clip you are going to evaluate with a similarity match.
Yes.
And LLaVA you're going to letting it output. So like there's another factor of whether the model is making correct predictions, including whether it can understand the instructions there.
Yeah. So yeah.
And also I think in one of them, if we evaluate in some way that leverages the feature more confidence relationship, it can actually perform at least better. So like using similarity matching is actually a better like tool for getting a higher score, but I don't think that should be a solution for us to getting a better score on the benchmark.
Oh, you mean that use similarity for LLaVA?
Yeah. But I think since LLaVA 1.5 is a language like vision language model, so yeah, it's fair to use like natural language output to evaluate, and we should not use a method that's not the way that people are going to use it to evaluate it just to get a higher score. And I think this is a proper evaluation.
Yeah, what do you mean by similarity? It compares similarity between the visual.
Like this image match this caption. And
yeah, that's right.
Answer yes or no, and you can get a confidence score for yes.
Yes.
For both sentence A and sentence B.
Yeah, that's right.
And then you can compare the probability
between
A and B.
Yeah.
Are you on that paper?
Yeah, I'm on that paper. Yeah, but essentially here I'm using text generation, but what Haotian suggests is use some probability to measure it.
But I think this is the correct way of doing it. Yeah, we should not try to get a higher score and just not use it the way that people are going to use it.
But even that, this table is not fair for LLaVA, because clip and LLaVA here is evaluated in a different way.
It's fine. Yeah, let's move forward. So the question is how can we fix this problem? So they are random. So can we fix this problem to get a appropriate performance? So I still come from the data perspective, and the most useful data strategy should be counterfactual reasoning. So this is a terminology in statistics, but essentially in simple terms, what do you need? You need positive A examples and negative A examples where they both can be images or captions, and then you have two or at most 4 pairs of counterfactual A examples, and you can train a model on it. So we designed some data curation pipeline for this approach. For example, for position for left and right, like the positive caption and the positive image is like what has already been provided. In order to generate negative caption, we just flip the keyword from left to right, from right to left, and then for the image, we just do a simple flipping to flip the bounding box. Then for above and below, this is a bit difficult because you can never flip an image vertically because it doesn't exist in real life, right? How do we handle this problem? So essentially, we shift the location of those bounding boxes and use a grounded image generation tool from our group called Legion to generate a new synthesized image with the specified bounding boxes, which empirically we found that helps the model a lot. And for counting, we also use a grounded image in painting, but here we use a very simple strategy where we replace some of the bounding boxes with trees, where tree can appear both indoor and outdoor. Yeah. Yeah, and for attributes like we can also encounter case like a man with blue hat and orange hat versus like a man with red hat and orange hat. West such kind of complex case where we replace some of the adjectives or nouns. So here we use the most advanced generative models for text to generate the negative caption. We use GPT-4V to guess what is the possible negative caption. And for negative image, we use the currently most advanced textual image generation model, DALL-E 3, to generate the image. And then we are done. After we have the data, we just feed the data to the original clip and LLaVA training or fine-tuning pipeline. Where for constructed models like clip, we just feed both positive image, negative image, positive caption, negative caption, and they naturally form the pairs in clip. And in LLaVA, we just use the original text generation laws to formulate the problem into a like multi-question, like multi-choice answer formulation. Yeah. Yeah. So how well does our approach work? Here are the empirical performances in positioning and counting. Like, so previously clip is among the random chance, and but after adding the counterfactual training data, the performance improved by 73%. And for LLaVA, the final performance is even near perfect. So for positioning, we also improve a bit, but it's not perfect. Yeah. Also in attribute reasoning, after adding the additional fine-tuning data, we also improve around 4.9% in both clip and LLaVA, where in the same evaluation setting, after adding the data, we finally have surpassed GPT-4V in this task. And here are some qualitative examples where the red means that the answer is wrong. Yeah, and we found that for those interesting examples, like the boy is with shoes or without shoes, white shirt, black shorts, or black shirt, white shorts, zebra has are far to each other or close to each other. Those questions, after fine-tuning, our models can answer it correctly. So then the question is why the data is so effective. So my guess, and maybe this is not important. My opinion is that the current large models are smart enough to learn the relationships or the knowledge given the high quality data. So maybe the most efficient way is that so previously the non-compositional visual concepts may live in the high density region like here and there. For example, clip may have a lot of captions like, oh, I'm wearing a red hat, I'm wearing a blue shirt, but they don't have a dense region where we can have like a blue hat, a white shirt, blue hat with yeah, and such compositional data may live in the low density data regime, and we found that after fine tuning specifically on those regions, we can get much better performance. Yeah.
After fine-tuning, we know that the trained model will perform better. But have you evaluate the model of the original ability?
Yeah, I evaluate and I can. Okay. Yeah, let me find the table. So yeah, here is the performance on the original like Coco retrieval task. Like after adding our method, the performance is consistent, somewhat high, somewhat low. Like here is the imaging retrieval, here is the text retrieval. Yeah, and if you really want to maintain the original data, I recommend use a data mixture to include both the original training data and your new data to get a balanced performance. Yeah. So yeah. So here is my second work on composing the captions. Yeah. For vision language models. Yeah, and it again demonstrates the powerful how powerful the data is in counter large models. And I will last finally I will introduce a work for large language models to understand the visual world without using a visual encoder. So this may sound scary to you because without the visual encoder, how can we fit the images into the large language model, right? So let's recall how clip or LLaVA understand image. So LLaVA have when a raw pixel image is fed into the large multimodal model, it will go through some clip encoder and NLP to get some tokens, and you can think about that those visual tokens are equally living in the same space as the text token. So this is how it works. Then a crazy idea is can we directly embed the visual information into a text, like a real direction is here. Can we directly go to this direction? So yeah, that means that we don't have a clip visual encoder and we don't have a connector, and we want to directly convert the pixel level information into the text. So the most straightforward approach is that can we convert it raw pixels directly into the text prompt? And here is an example. So this solution is I think it's sort of unfeasible because like you have a huge matrix, especially when your image resolution is high, and for each pixel it will be some integer or floating point. Yeah, and then there is no semantics into in the image. So yeah, we tried this approach and it didn't work at all. So and it shouldn't work. So then we need to find a ways to simplify the images. Because we all know that the visual information are redundant. So like artists, let's learn from artists like Picasso. So here is a famous drawing from Picasso where there is this is a result ox, and then Picasso simplify and got this. And it's interesting that we human can recognize that, oh, this is an ox just with several sketches. So we believe that if the human can understand it this way, then can large language models also reference the visual information in such sketch style. So what is the format to depict the sketch in visual? It's called a Scalable Vector Graphics. And here is an example, and SVG can usually be found in some icons, like if you find the icon for Madison, for BMW, for Google, the icon is usually SVG. So SVG is called vector graphics because it has vectors. So it includes some sketches or some circles. Like for circle, you need to define the center, like the radius, and for rectangle, you can define the width, the height, the center. Yeah. For lines, you can define the starting point and ending point. So finally, with such visual elements, you can compose an image. Yeah, go ahead.
Two questions. First, why do we want to make large language model directly understand the image without using the vision encoder? And second question is, that all the images can be represented by scalar vector graphics? Because I feel like most of the images available online there, like PNG or some other format, right? Can they be directly transformed to scalar vector graphics?
Yes, those are the two most important questions I think in this field. So why do we explore this direction? Because yeah, that's old memory. That's from 2023. Yeah, that's from the March in last year, and at that time we saw that GPT-4 is so excellent in processing text, and it just motivates us to understand whether the large language models can also understand such image in a certain way. So this is an exploration out of curiosity. Yeah. And secondly, how do we represent the real world image? And here you can here is an example where you feel like this is the real image. So in order to convert the natural images into SVG, you need to have some geometry primitives, meaning that you need to have some basic shapes. So what we do so is that we use a segment model called the segment anything, which will convert the image into a set of masks, and then we convert each mask into the polygon, which forms the SVG.
I see. Actually, before I also had work that used large language model to handle non-language tasks. And we just use the stupid method, like convert the images into pixels. Yeah, and as you said, it is too long, and we only test on the smallest image data set. It works there, but not for others.
Yeah. In the experiment, we also compare with your approach. So
Okay.
yeah. Let's wait to see what will happen.
What are the criticisms from the reviewers to it?
Oh, because that paper is not about using language model to handle image. We just find that it works for images. So it works for MNIST, and we didn't test for others. We just tried to do like most of the tests about tabular data set.
I see.
Yeah. So after we have this SVG format, we found that it has several benefits. The first benefit is that it naturally avoids the problem of very long row pixel representation because SVG has infinite resolution. If you zoom it to infinite times, it's still clear. It's not mosaic because it's vector, it's not pixel. And secondly, this kind of text format, we empirically found that it can be integrated or interleaved with natural languages to do the task, like both image understanding and image generation. But note that those capabilities currently is far from like the approaches using powerful visual encoders and generative models like CLIP or diffusion model. But there are some interesting phenomena that we can observe from SVG. So here is a prompt engineering example we did in last March. Like we prompt GPT-4 to like colorize this app, and GPT-4 can give you the correct SVG code about this apple. So let's think about how many steps is needed here. The GPT-4 model need to first do a perception task, like categorize, which part is apple body and which part is leaf of the apple. And then the model needs to do the generation task, like replace which color attribute, like replace the body from black to red and replace the leaf from black to gray. And then we can also do some interactive generation or editing, like make the steam brown or make the left half of the apple body red. So this example demonstrates that SVG can somehow have an understanding about the large language models like GPT-4 can somehow have an understanding capabilities about SVG, but we should quantify this understanding capability. So firstly,
is the original like black apple contain the left part and
yes,
the right part?
yes, that's right.
So is the last image the original image, and you just remove all the colors and feed it into the GPT-4?
No, actually, this image is original image.
Oh,
But it can the body contain two halves.
oh,
So we replace all colors to black to do a reverse engineering to
And
see
for-
what will happen.
so for the left part, like, is it a single element is sufficient, or it's actually composed of like multiple half squares?
It must contain multiple elements because here is a line, here is like some part of this is the circle, here is some part of circle, here is a line. Yeah.
So it's actually like even for the last one, there is like maybe more than four, like maybe 10 or 20 sub elements.
Yeah, we found that GPT-4 can process like more than at least 4 or 5 elements. Yeah.
That's cool.
Oh.
So how many components that most of the images in the data set you use? They have how many components that most of the real images have?
Okay, so for this question, like if you consider the images from the designers or artists, usually the components are very few, because the visual data has been condensed by the human brain to certain parts. But for natural images, it's very difficult. Why? Because the content segmentation model is not smart enough. Like if you have an airplane, it can segment every small part into an individual part. But we human may just draw a sketch for the airplane, but the content segmentation model is not smart enough. So for natural images, it can lead to unprecedented. It can lead to very long context. So SVG currently do not perform well for natural images.
Even for this image.
No, for this image, GPT-4 can work because the thing is very simple. Yeah, if you have the complex thing like what I said, what I used initially, like 10 people standing in a scene, then it wouldn't work because the sequence length is too long. Yeah. So starting from now, I will show some quantitative measures about SVG understanding. So firstly, we do a simple visual reasoning task. The task is called sort of clever. Sort of clever means that it's not so clever. Why? Why? Because the original clever task is constructed by the 3D objects, like they use some graphic tool to place certain objects into the table, and then use different camera views to capture the 3D object. But here, the problem is simplified that so that the objects are placed in a 2D canvas, and the object only have two shapes. I think, yeah, the square and the circle. The color there are 6 colors. So here is the problem setting, and here are 3 kinds of reasoning question. Like what's the shape of the green all objects? How many objects have the same shape as the red object? Is there an object lies on the line that connects the blue and the green object? So here the model needs to do some mathematical geometry questions in order to solve this problem.
Why is the answer yes?
Is there an object lies on the line connecting to? I don't know which question does this, which image does this question belong to? Maybe this one, but those questions are for demonstration. Okay. And in addition to this, we also do some auto distribution test examples. Like in CNN, if you are only trained with such images, you can never do problems like, what if I make the circle flat? What if I add additional colors like black or pink? Can the model still answer the question correctly? And here is the experiment table. So the take-home message is that the GPT-4 chin or short with SVG format here, it works best for both in distribution and OD cases. And some interesting findings like for traditional approach like the closed word, CNN or relation networks, they perform good on in distribution. They suddenly perform bad on the auto distribution. Yeah, but for GPT-4 vision, the performance keeps consistent upon different cases. So this tell us that for some simple reasoning cases, GPT-4 with SVG has some advantage over the PNG format. And yeah, and here we and previously it's a discriminative task, and here we do a generative task. So it's the task is called visual prompting, which is a task in image generation. So this is also related to in-context learning, where both the key and value are pixel level images. For example, given such two demonstrations and a query image, the model needs to generate the corresponding resulting image. Like it should be look like this, and also we can switch attributes like we change the shape, or we resize it, or we use the combination of such attributes. And then how do we evaluate the performance? We can just use pixel level MIOU to evaluate how good a model is. And we found that among those cases, GPT-4 with SVG performs best compared to the previous pixel-based approach like MVE, VQGAN, or BEIT. So yeah, here is another promising experiment that that SVG can, along with large language model, can solve such basic reasoning task pretty well. Yeah, and here we go to the here we go to the real images section, and we jump to MNIST. So we select MNIST because it's standard and it's simple. We again do the auto distribution test case, like in original training and test set, your MNIST image is always black and white. But here we can choose the foreground and background color. Like we can produce the easier case called color MNIST A, and more difficult case like color MNIST B. So here is the performance. We fine-tune Vacuna based on the SVG format, and we also fine-tune Vacuna under the PNG, which is the low pixel format, and this is what Yuchen's approach is. Which is just fit all the pixels into a large language model. So let's compare the performance for MNIST test set. All the models perform pretty well, except that if we prompt SVG here, there is short format to GPT-4, the performance is pretty low. Yeah, this also demonstrates that GPT-4 is not able to understand the natural images right now. But if we focus on the connex, I think the currently one of the most capable vision backbones and the Vacuna, which is the language model. Yeah, for in distribution, the performance is nearly the same, but for auto distribution, there is a huge difference. Like when we fine-tune Vacuna in the PNG for auto distribution, the performance degradation is very huge. But in SVG, there is some degradation, but it's not that huge. And Connex is somewhere in between. So that's the reason why SVG could perform so good, so well on this task. This is because SVG explicitly decompose the color with the shape. So like in this case, if you change the format, like if you change the background and foreground color, then every pixel in this image, its value will be changed. But for SVG, the only attribute that have been changed is the color. So SVG is naturally a kind of format that can define such a color attack in test time. Yeah.
Yeah, I have one question. Is the image in color MNIST A and B and also original MNIST have like one-to-one correspondence?
Yeah, one-to-one correspondence. We just use the mapping, like for each image, we map all the pixels which has value higher than 128 into 1 and R right into 0, and then we colorize such binary marks into different colors. So it's a very fair apple-to-apple comparison.
And when you like are training the model on the MNIST data set, are you saying that color equals to white and color equals to black?
So for all those methods during training, they are only able to see the image with black and white.
No, I'm trying to understand why there is a performance drop, because if the model never uses the color to.
Oh, okay. So even in SVG format, there should be a attribute of color.
Yeah.
Yeah, because in test time, even though the coordinates or the shape keep the same, but the color attribute changes, so the distribution changes a bit, and I guess this is the reason why SVG there is a performance degradation. Yeah, go ahead.
We tested to have like digits have multiple colors. Or have that different colors. So
has the image with different colors.
like 2 is currently green in the rightmost image, right?
And
the red is that is 2 colors.
Yeah, here it has 2 colors. Yeah.
Like every image is, yes, there's 2 colors. But
Yes.
3 you could have half of 3 as a red and half of 3 as yellow or something like that.
Yeah, that's a crazy experiment. Maybe we can try if we have time. Yeah.
There's actually a data set that does this called MNIST M, I think. So
Oh,
weird streets across the.
oh, it's very wild MNIST, right? Yeah, that's usually. Okay. Yeah. Yeah. Also, we do some interesting in-context prompting. So this is not a quantitative example, just qualitative. Like, so when you prompt a GPT-4 with English characters like 16, 36, 20, 25 or 15, it's very easy. But here we convert the English characters into SVG. So for the input fed into GPT-4, this is actually an SVG image, and this is also an SVG image. So in this example, we have 5 SVG images as the input, where 4 of them are demonstrations, and the model needs to predict what should be the value or what should be the answer. So we can find some interesting phenomena like, for this case, the model can guess that the only possible math operation is multiplication by 2. This math operation is the addition with 12. And then this is the deduction. But the last 2 are the most interesting one. So if you give one in-context demonstrations, then the math operation cannot be the single one, right? There can be a deduction operation, right? Deduct by 7, which is this answer. And there can also be some multiplication operation where the answer is 8. Yeah, similar thing happens in the last example where we can have some multiplication and addition. So Yeah, so the take-home message is that SVG plus SVG with the math operation can also be understood by GPT-4V.
Do you tell GPT-4 that it's a SVG of like number digits, or you just say solve it or complete it?
I remember it's a later case.
Oh, solve it.
Yeah, I remember.
Oh.
It's
That's easy.
I have one question, like, it is possible that GPT-4 will train on a sort of like HTML format?
That's right. This is what we guess because SVG belongs to the family of XML, and XML can be used in formatting in a similar format to JSON and even in website. So there are many available data set in GitHub, and people see that OpenAI they use GitHub source to train their model. So I guess the GitHub code is the source of intelligence for SVG. Yeah. Here is an example about understanding natural images. Yeah, and that's it. So we saw that SVG is good at understanding the basic geometry or simple question, but there is a large gap for natural image understanding, like ImageNet. Yeah, we do the experiments on ImageNet 10 class classification, and SVG is inferior than RedNet 15. And the gap is 20%, and this is a huge gap. So we can claim that, oh, SVG is not naturally suited for this task, but I think what we may need is that so GPT-4 don't have a lot of vector graphic data. So what if we collect a large scale of SVG data and train a text generation model on it? Can we exhibit even better behavior than GPT-4? So yeah, I think this is an interesting topic to explore. And that's it. Yeah. GPT-4 is the closed source.
But I also like, I mean, if we have the tool to train the model with SVG data or with images data.
Oh, okay. Yeah, that's your question. Yeah. So I think with pixel data is more suitable for this approach to understand natural images like ImageNet or the photo captured by your phone. But SVG, actually, this area is very active. Like if you read through the paper list in SIGGRAPH, there are some papers use SVG as a source of the data in deep learning. Why? Because a lot of designers and artists, they use SVG to design the logos or signs for companies. So let's say if we can build a text generation model that is beneficial to the designer. For example, the prompt is, please make the Google logo more cute. And then the model can generate a new Google logo. I think this will at least be very useful to that group of people. Yeah. Yeah, any other questions? Okay. Yeah, thank you.